Just started it.
Dope. All right, it feels like a good enough time to start. I think everybody that is going to be in here is in here. We have 25 people. That's good enough for me. Cool. Welcome to the review session. We're going to be covering most of what you should know for the quiz and then going through the entire midterm practice exam he gave, so we can cover that and I can explain to you kind of stuff you should keep in mind. So let's first of all talk about how the midterm works. So the midterm will be a PDF with exercises and a Canvas quiz. You're basically going to write your answers down on the PDF, like normally, like you would do a homework, and then you're going to submit your answers to the Canvas quiz. The reason you do your work on the PDF is in case you get something wrong, you get some partial credit. There will also be a small coding project, nothing too hard. That's all I have from him. So good luck. It shouldn't be too difficult. It'll be in Python. You should be good. You will have all day on Friday to do the quiz. The quiz is open everything, but do not copy paste off the internet or other students. Pincheroli is watching. He will find out. He has tools to check your code. Do not plagiarize on your code. It is a dumb reason. Cool. What's going to be on the midterm? Your midterm is going to be on lectures 1 through 7, basically everything up to A star. Hey, Mylan.
Sorry.
You're good. Cool. It's everything up to A star. You're going to be covering differential drives, forward and inverse kinematics on that, some ROS stuff, how ROS works, some basic ROS commands. You might have some map stuff on there. I'm not sure. I'm just going to really quickly cover occupancy grids so you guys have an idea. And then graph search, where you're going to have BFS, which is wavefront on an occupancy grid, DFS, Dijkstra's algorithm, greedy breadth first search, and A star. Those are the things you need to know and know how to do them. Okay, cool. Let's start off with differential drives. These are the main formulas you need to know for differential drives. Keep them in mind, write them down on the formula sheet, or know where they are located in the lecture slides. You're basically going to be doing a problem similar probably to like homework 2 or to the midterm. So something along those lines. If you know how to solve those types of problems and you can do homework 2 with pretty ease, you should be okay. We'll go through the example on the midterm a little bit later. Here are some more formulas you might need to know. Write them down, keep in mind them, make sure you have them somewhere to reference. The basics of ROS stuff that you should know what a publisher and subscriber are. You should know how topics and messages work. You should understand that ROS is a bunch of nodes and the nodes communicate through topics. You should understand how services work and what a service proxy is. You should understand what the ROS master is. You should understand how to call the ROS master. You should know what catkin is. You should know what ROS packages are. And you should know these ROS commands. You know how to launch nodes with ROS run. ROS launch should be launching ROS files. RQT graph will be showing you your node, like a visualization of your ROS system. So like all the nodes and topics in between them. You should know how to use ROS topic to echo or info, get some info about the topic. You should know about ROS what the fuck, because ROS what the fuck. And you should know about ROS core, which will launch your main ROS master. And you should know about ROS node and catkin make, which builds your workspace. Maps in this class are generally stored in an occupancy grid. Keep in mind there are other ways to store maps that are generally better to have the map in, but are harder to compute, which is why we use occupancy grids. When you are doing path planning in occupancy grid, your paths are not optimal and not complete. The algorithms we are using may be optimal or complete, but the path themselves is not, because we are essentially taking a space of like a square and turning that into a single point, and therefore you kind of lose some resolution. So just because a path doesn't exist in your occupancy grid, it may actually exist in real life. It just may be that you have to cut through a square or something. So that being said, we still use them anyway because they're a pretty good way to do them, and if you make the resolution small enough of the grid, it doesn't really matter too much. But do keep in mind that they are not optimal or complete. Non-optimal means that the path that you generate is not always like the ideal one, and not complete means that every possible path in your actual world exists in your occupancy grid. So your occupancy grid kind of is like a shittier pixelated version of the real life grid. And therefore you kind of lose some resolution and therefore lose some ability to plan paths. And that's like an important thing to know about occupancy grids because they seem kind of like magic when you like get used to working with them. All right, let's talk about what breadth first search is. So I think the better way to, couple things to keep in mind about breadth first search, we'll just kind of go over briefly and then I will, oh, my bad, I put the wrong, my bad. Okay, there's a mistake on the slide. It's supposed to use a queue. Breadth first search is used a queue. I was copying and pasting and I copied wrong. So breadth first searches are when you have a graph. Actually, we'll just draw it out here really quick. I'm going to switch over to who's sharing the screen and we will share on the iPad. Give me 1 second. Share content, screen, start. Yes. Ta-da, iPad, nice, okay. Cool. So breadth first search is essentially, we'll draw like a quick little tree here of some nodes and kind of give you like the high level overview of what breadth first search is doing. And then we'll like kind of cover in detail what how exactly it works. So when you're talking about a breadth first search, the best way to think about it is kind of searching layer by layer from your start node, right? There's a thing in the chat. What is the thing in the chat? Never mind. All right. Yeah. So you're starting kind of layer by layer, and you are kind of searching from essentially your start node, assuming this is your start. And then you are kind of searching layer by layer. So you'd be searching the first layer, you search them, then you would search the second layer and search all of these in order, right? This is a pretty important concept to keep in mind. The way this works is that, like, if you go back to Pincheroli's like pseudocode that he gave you, he's using a queue, right? So it is a first in, first out data structure, right? So essentially every time you search a node, so let's say you were searching, let me backspace all these. We'll label these real quick. So let's say you're searching this node here and you have your queue. You would take your node and you would put them in the queue. You pop the queue, say, okay, I'm searching my node right here. Okay, then I'm going to add its two neighbors. We'll call these guys B and D. So then you add both B and D in alphabetical order, and then you get rid of the one that you've already visited. Then your next iteration of your loop, you're like, okay, well, what's my next node in my queue? Oh, my next node is B. So then you pull out B and you look at B and you add B's neighbors. So we're gonna call this one C and E. So then you add both C and E to your queue. You pop out B, B's gone. Now, next iteration, you're like, okay, what's the next node to search? It is D. You add D's neighbors, which we're gonna call F and G, and so on, right? So essentially, the big thing to keep in mind is the order that I put things in is the order that they come out, which means I end up searching layer by layer through my tree. This will make a little bit more sense when we go to the example problems. This method, that data structure that I was kind of drawing, is called a queue. The opposite of a BFS is a DFS. And we'll cover that in a second, but there's a couple more points I want to make about breadth first search. And that is that breadth first search is optimal and complete, provided that the graph is non-weighted. So a breadth first search is optimal, which means it will find always, in every case, find the shortest path between two nodes, provided that the thing you are trying to optimize for is the numbers of nodes, like number of nodes that you search. Right, so it is optimal and it's complete. That means it will search like every possible path. So it will, there's no case where the BFS will not find the path if the path exists. That makes sense? Cool. So let's talk about the depth first search. So the depth first search is just like a breadth first search, to the point that the code bases for them are identical. The only difference is the data structure that you put them in. So this one uses a queue, and depth first search uses a stack, right? And so what that means is the order that you search the nodes in, rather than being layer by layer, is you kind of travel all the way down the tree. So we'll draw like a little example of that in a second. Other things to keep in mind about depth first search is depth first search is complete. That means if a path exists, depth first search will find it, but it is not optimal. It will not always find the shortest path in an unweighted graph, right? So you may have a case where it finds some like weird roundabout path, but that just happened to be the path that it went first. So let's draw our little graph again and perform a depth first search on it. So we'll call this A, B, drawing is hard, okay. C, D, E, F, G. Cool. So the way your depth first search is working is what goes in is the first thing to come out, right? So you put an A to your thing right here, and you add in A's neighbors. So you're like, okay, now B goes in. Now you're in B, and you look at what's B's neighbors. B's neighbor is D, right? So now that you hit D, and you say, okay, what are D's neighbors? Oh, D's fully explored. So then we remove D from the stack, and then we say, okay, we're back on B. What's our last thing? That's E. So that's our next node. So we've gone, essentially the way to think about it is it goes down, all the way down one branch of the tree, up, back down, back up. And it kind of follows this pattern of exploring all the possible, like all the way down a single root, like all the way down a single branch of this tree, which is why it's not optimal. So some other things to keep in mind is that DFS is pretty computationally good. It actually, once you've kind of explored a tree, you don't need to keep track of that tree anymore, so you can kind of wipe it out of your memory. Meanwhile, breadth first search is very, very computationally heavy, right? You have to store the entire tree and the entire graph into your memory, which is problematic when you are doing big, big graph searches. We're going to go over another example of doing these things in a bit more with Dijkstra's and stuff like that, but just know that it is basically, they're the same thing, just switch a queue to a stack. It is one line of code change, and you can replicate the change of behavior completely, which is very beautiful in terms of code. All right, let's go back and start talking about weighted graphs now. So in both these cases, we were talking about an unweighted graph, which means like this edge value, like the distance to travel from any one node to any other node, is of no weight. It's the same cost regardless of the node. But that's not how real life works. We have terrain and we have walls and other stuff in the way, so we need to keep track of that. So the next thing we're going to look at is our weighted algorithm. So let me share my screen again. Yes. Cool. Okay. So the next three algorithms I want to talk about are Dijkstra's algorithm, greedy breadth first search, and A*. So Dijkstra's algorithm, it is BFS, but now we modify it a little bit. Instead of putting in a queue, we put in a priority queue. And now what's the difference between a priority queue and a queue? Well, a queue is just first in, first out, right? So it's just, you dump things in, they come out in the same order. A priority queue is a structure where you put a thing in, and you put another thing in, and you give them some sort of weight. Then the queue sits there and goes, okay, what do you want to take out? And the queue says, I'm going to take out the smallest weight. So whatever the smallest number attached to my value is, right? And how do we determine that weight? Well, in Dijkstra's case, we're going to choose the minimal cost node to travel to, right? So there's this function g of n, and that function describes the cost to get from our start node to our current node, so our current node being n. BFS, or Dijkstra's algorithm, and the priority queue will choose to pull out the lowest cost node first. So what are the important things about Dijkstra's algorithm? Dijkstra's algorithm is complete. That means if there's a path, it will find it. It is optimal in the case that all your costs are positive, which means you don't have like negative costs or that your costs don't like go down. What's the con with Dijkstra's algorithm? It's not super efficient, right? The problem is you're searching all of the nodes that are close to your start node first, and it kind of takes ages to find the thing, but it will find an optimal path. So can we do any better? The answer is yes. We can do a greedy breadth first search. The greedy breadth first search is just like Dijkstra's algorithm, except we change our cost function. So now instead of choosing the cost, that's how far from my node is my start node, we try to write this heuristic, or like this h of n function. And this h of n function is an estimate from our current node n to our target node, right? So in the case of our robot, we're using Euclidean distance, which is not the exact cost, but a pretty close estimate. So it ends up working out. Some stuff to keep in mind. Greedy breadth first search is a complete algorithm. It will make sure to always find a path if a path exists. It is faster than BFS, but the paths are not always optimal, right? There's a chance that your heuristic function is off, and then you kind of lose optimality, which is right? You're also not really keeping track of like which node is closest to like your start node. So you may end up like just choosing some like really ugly path to get there, but it's the fastest one. So can we do better than this? Well, we can actually combine the two, and what we get is A star. A star is if you take greedy and you take Dijkstra's and you just slap them together, and you're like, you are a new cost function. So your cost function that you're putting into your priority queue is your G of n, which is your cost function from Dijkstra's, plus your H of n, which is your cost function from greedy breadth first search. Things to know about A star: it is a complete function. If a path exists, it will find it, just like the rest of these. And the optimality is a bit weird here. So a term you need to know is admissibility. Admissibility is that the function H of n, which is your estimation function from your current node to your end node, never overestimates the cost, right? It's optimistic. If it never overestimates the cost of the goal, then A star is an optimal algorithm. If H of n is not admissible, or it does overestimate the distance from your current node to the goal, then A star is non-optimal, right? And as you kind of change how close or what that value of H of n is, you can kind of replicate other behaviors. So if you set H of n to 0, then you have Dijkstra's algorithm. And if H of n is way overestimating the cost of the goal, then you have greedy breadth first search. So those are the algorithms you need to know. That's like the core, like that's like the high level overview of what they are. We're going to go through the examples next. But before I do that, are there any real questions on that stuff?
Can you go back to the Ross stuff? I think it was like the second or third slide where it's like the yeah. No, back one more.
This stuff.
Yeah, that stuff. Can you just do a quick little run through of those guys?
Of like what they are?
Yeah, just like quick theory definition type stuff.
I mean, Ross master is the easy one. Ross master is your like master node. You have service and service proxies. Services are a system that allows node to node communication and kind of back and forth communication between two nodes. Publisher subscribers are the core communication in Ross, right? You have topics, which is where you publish to a topic and subscribers listen to these topics. You can have any number of publishers and any number of subscribers. Messages are your standard format for talking on these topics. Ross packages are how you define stuff in Ross. So like essentially you can make a Ross package to like bundle up various Ross components, and Kaken is the thing that does that bundling. Did I get anything wrong, Cooper? That all sound right to you?
That's all right.
Cool. I was doing that from memory, so I was hoping I'd get that right. Any other questions on the Ross stuff or anything else really? No?
Mylan has a question in the chat.
I cannot see the chat, but let me look and see if I can. Buttons.
It just says, "Where are you?"
I am in my bedroom. I don't know. Okay, well, yeah, I'm in my bedroom, in case anybody was wondering. But I don't think that's what she was asking. Okay, well, Milo, do you have a different question or is there actually clarification to that question, or did I'm going to assume that was an accident otherwise? Cool. I'm going to assume that's an accident. Okay, let me share the iPad and then we will move on from there. Okay. What am I wearing? I'm wearing clothes. Okay, we're gonna. Okay, how do I share things? I know things. Hold up. Okay, share content, screen, start broadcast. Yes. Okay, more chat. Look out your window. No, never. That sounds like an awful idea. Okay, cool. Let's go into example problems. Everybody's favorite example problems. Okay, So our first example is going to be the exercise 1 from our homework. And the question is basically, you are given a differential drive robot with a 30-centimeter wheelbase. Suppose that the robot is initially located at the origin of the coordinate system. So we'll just call that, and the robot is there at 0, 0. Robot. Cool. And is initially oriented at pi/2 relative to the x-axis. So he's pointing this way. I'll use a different color. We have the technology. Okay, he's pointed that way. Given that this axis is x, this is y. Cool. And that your task is to drive the robot forward along an arc with a radius of 8 meters to the point 10 meters, 10 meters in 20 seconds. Cool. So he's trying to go here. And there's some radius, which I may not end up using that radius. We'll see in a second. And that radius is a value of 8. Okay, cool. Well, the easy question, what are the wheel velocities required to reach point 10, 10 in 20 seconds? So we have our two formulas that we need to use that you should keep in mind. VR is equal to omega r plus L over 2. And VL is equal to omega r plus L over 2 minus L over 2. I can read. Minus L over 2. Cool. We have those two formulas, but we want to use. The thing is, we need to calculate omega. So what we need to do is find the omega t, or omega times theta, calculated, covered in 20 seconds. So what we first need to do is use the law of cosines to find the omega. So if you remember, we're going to start naming these points correctly. So we're going to call this one O, we're going to call this one P. And so we can use essentially OP squared equals OC, OC being our center. Right, I have that right. Yep, okay, we have OC squared plus PC squared minus 2. I did not write this in the right place. God damn. Okay. Minus 2 OC OP times the cosine. Come back. Okay, we're gonna put this here because reasons. Cosine of omega times t, change in time. Okay. Remember, C is going to be our ICC. So in this case, C would be somewhere around here. And what we can calculate, if we solve for omega, I'm not going to go through how to solve for omega. I'm assuming you people know how to do basic algebra. If you don't, God help you. Omega is plus minus plus minus over 1 over delta t times the arc cosine. Wow, the writing skills. Also, my handwriting is really messy, and I'm super sorry for that. The arc cosine of OC squared plus PC squared minus OP squared over 2 OP PC. Keep in mind, these are distances that, like, I'm writing. These are like the magnitudes of those vectors, just so that's clear if that wasn't clear earlier. All right, plugging in our numbers, we get omega is equal to plus minus 1 over 20 of the arc cosine of 8 squared plus 8 squared minus 10 squared plus 10 squared over 2 times 8 times 8. Cool. The way we calculated those distances was literally, you draw your ICC, you know that your ICC needs to be at a radius of 8, which defines OC and PC, right? It's a distance from P to this C point right here. And our OP is determined by this Euclidean distance, right? So you just do the hypotenuse of that.
Arjun, I've got a question for you.
I have an answer.
I could be dumb, but is the distance from point P to the ICC actually 8?
Yes. Do you know how we know that?
No.
We calculate that because we were told it in the problem, right? So that radius that they asked for of 8, it becomes that distance, right? So let's draw this diagram bigger here. That's awful. That's just the worst. Okay.
Also, Arjun, why do we have 2 8 squareds and 2 10 squareds if there's only like 3 vectors?
So I'll let me explain that in a second. Okay, cool. So we're gonna call this 0, 0, call that point O, and we're gonna call this P at 10, 10. All right, and then we're gonna define some point here. We'll call it C. That's our ICC, right? All right. So the important thing in the problem is they said, okay, here's our radius, right? And a radius of a circle said that, hey, these two lengths must be equal. And they said that this R must be equal to 8. So this distance between PC and OC must be equal because they are in a circle, and their value must be 8 because the problem told us that they want a radius with the circle 8 or a radius of 8, right?
Right. So then I guess I got a follow-up question.
Yep. And go ahead.
Because the robot is facing straight upwards and the ICC is either to the right or left of the robot, depending on the direction it's turning, shouldn't the ICC be on the x-axis?
No, the direction that the robot's facing right now kind of doesn't matter. Right. They're asking what wheel speeds do we need to set to perform that arc. So we don't actually care what direction the robot is facing. The assumption is we can kind of just like turn into it when we need to, right? Because you're not going to be facing the like straightforward may not be the optimal direction to be facing to actually do this radius.
Gotcha. So that angle doesn't actually matter. It's just
that this angle theta is just like arbitrary because I just drew like some arbitrary point. Like I drew some arbitrary point here. So this like theta or whatever like isn't really relevant or matters right now. Right. That C is just at a random point that like seems relatively correct. So the diagram looks good. Right. So if we're looking at now, what we're looking at is the actual law of cosines formula. And how did we get these 8s and these 10s, right? So the first thing we're solving for is OC. So this distance is going to be 8 squared, right? Because R squared, OC is equal to R is 8, so R squared. Plus another R squared, right? So that's going to be 8 squared from PC, minus OP squared. So OP squared is this line right here. And the way we calculate that is the magnitude of that is equal to is just 10 squared plus 10 squared, right? And then you square root that technically, but since we're doing vector math, we don't need to. Or it's squared. So sorry, I said it wrong. It's squared. You do square root of the distance is equal to O to this. That's 10 squared plus 10 squared, 1 for X, 1 for Y, right? Then you square that entire thing and the square root goes bye-bye. That is the explanation, sorry. That makes sense of how we got those numbers?
Yeah.
Cool.
Arjun, would this formula for omega work for any problem, basically?
This formula for omega, it should for any problem that is structured like this.
All right.
Yeah, it's the law of cosines, right? So you're using the law of cosines to calculate your ICC and then substituting in your omega. Like there's kind of both those calculations baked into one. But you could like solve for your ICC center and then like try using that instead, but then you get the same equation basically. The law of cosines is like kind of how you would attempt to solve these problems. But basically, if we solve that out, we get plus minus 0.11 is that question. The other question that we have is, what is the pose of the robot when it reaches point 10, 10? So there is 2 ways to choose this. We could either have a arc that looks like this or an arc that looks like this. The reason we are choosing the upper arc instead of the lower one, or a negative rotation, right? So your XY goes this way, and then you can't see my hands, but this upper arc is a negative rotation and the lower arc is a positive omega. So we're going to choose the negative omega in this case because your robot is closest to that. So the simple way, the first thing we need to use is find our ICC, right? So we have our ICC at, or well, there's a formula we need to be using to calculate the position of your robot, and that involves using the ICC. So you have ICC X and ICC Y, and that is going to be equal to X minus R sine theta p, which is our position. And then we have y plus our cosine theta p. These equations are in that like thing that we have up above or in like lecture slides, and I'll post those as well. And theta p is the unknown orientation that we are looking for. So the easiest way to find our ICC is, because our next step is essentially, where is ICC? How do we solve for that? So I'm going to just scroll down a bit and then we'll come back to our equations in a second. So there are two ways we could do it. We could either use the formula that is x minus cx squared plus y minus cy squared equals r. And this will give you two centers. You can pick one of them. But there's another way to do it that's a little bit easier, in my opinion, and that involves using the vectors. So if we draw our diagram as follows, where we have an x-axis, or y-axis, sorry, and an x-axis, bum, 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 and we have our points O, we have our point P, we have a point that we'll call C1, and we will have a point called C2, which is going to be the center of our circle, and we can draw a little triangle right here. And then this. We're going to pretend that these lines are perfectly straight. And then we will draw a circle of the corresponding radius around. So this is an 8-meter radius circle, essentially, that I am drawing, even though it looks nothing like a circle. Just pretend that it is. We're going to label another point right here. We'll call this M. I should start using different colors. Let me just really quickly put all of the variable names and points in like some more easy to read color for you people so you guys can see. Cool. Okay. We will use like that. Okay. So we're going to call a point here, call this M. This is going to be our point P. This is going to be O. This is going to be C2. And this is going to be C1. All right. So C1 and C2 are both possible centers of our circle, which is why we have them there. So what we can do is we can use the distance of OM. So we do OM is equal to 1/2 of OP, right? Because you know that this midpoint essentially must be in the middle of OP. And so that is going to be 1/2 times 10, 10, which is our vector. And that gives us 5, 5. The other thing that we can figure out is that, no, what? Keyboard, okay. The other thing that we have is we have OC1 is equal to OM, right? So distance from here to here, plus the distance from M to C1, right? So this is the magical thing about vectors. You can just kind of add them together and they just work like magic. I'm assuming you guys know how to do basic vector math. This is something you learned in some class. I don't remember which one it is, but we can get these two formulas if we look at our diagram. Right? So this is just the distance from M to C1, distance from M to C2. This line is very off, and I just realized that. Apologies. Okay, I'll make that look more reasonable. Cool. That makes more sense. Keep in mind that C1 and C2 are equal distances from M because they're both possible circle centers. That is why I have them. So if we solve for these equations, and we kind of solve for M1 in this case, we can write MC1, the magnitude of that, is equal to the square root of OC1 minus OM1, right? So this is just solving equation 1 for MC1. Then plugging in the values that we know, our distance from O to C1 is going to be 8 squared. Our distance from M to C1 is going to be 5 squared. 5 plus 5. So and if we solve that, we get a distance of square root 2 times square root of 7. Cool. Also, by the way this is built, we know that MC1 and MC2 is equal to this, like they're like the same distance apart. So we can just call this length that we solved here as D. So now we can define some vector. We'll call him P. He is perpendicular to OP. And he has a length of 1. So if you want a length 1 vector, you just do brackets OP this. So you're just dividing your vector by the magnitude. And that gives you the unit vector, right? So then we can solve this. We get 1 over square root of 10 squared plus 10 squared times your magnitude of your vectors. And you get a perpendicular vector of 1 over square root 2 and 1 over square root 2, 1 divided by square root 2. Cool. And if we then solve the sign or like apply the plus minus to it or the perpendicularity, we get minus 1 over square root 2 and plus square root 1 over 2. Right, so these are just the two possible directions that the vector can go in. All right. We can then write 4 and 5, or in this case, 4 and 5, our equations up here. So we'll recall these up here. So this is equation 4, just for reference. This is equation 5. I forgot to write this down. All right, so we can rewrite those as the following. We can get OC1 is equal to OM plus D, which is our magnitude, times our vector P, right? So this is a vector there. And then we can get OC2 is going to be equal to OM minus D times that vector. Perfect. Cool. Then if we solve this out, essentially you plug in OM and you plug in DP, you're going to get OC1 is equal to 2.35 and 7.65. And you're going to get OC2 is going to be equal to 7.65 and 2.35. Cool. We can pick either center in this case, but because you're initially facing straight forward, you want to choose the one that would have to like correct its orientation the least. In this case, it's C2, because remember C2 gives us the nice big circle this way. So choosing C2, we can then solve for, let me pop back up here and grab some formulas that we're going to need. Where are they? I'm going to copy this, paste it down here. Cool, we have that formula. All right, so we can write theta P. So in order to solve for theta P using C2, we can write this formula right here, which is theta P is equal to the derivative of theta plus omega times delta T. Oh, sorry, I said derivative because of the symbol that was written there. It's not the derivative. This theta initial is just the orientation you need at the beginning to actually cover the path, right? So it is the initial orientation your robot needs to turn to. Theta initial. Why did he write it with a derivative sign? So theta initial, or yeah, okay, we're gonna call this like theta start or something. Theta I. So theta I or theta initial, which is the initial orientation we need to rotate to in order to calculate that trajectory. So if you remember, we have this trajectory up here. We're facing currently straight forward, but that may not work for our orientation. We need to be tangent to that circle. The way we calculate that is we do ICC X over ICC Y equals X minus R sine theta I over Y plus R sine theta I. Cool. Where Y and X are 0 because we're starting off at 0, 0. And from that, we pull that ICCX over ICCY is equal to sine of theta I over cosine of theta I. Oh, I wrote this equation wrong. I'm sorry. This should be a cosine. And that is negative because there's a negative sign up top. We've canceled out the R's. I just didn't want to write that down. And now we have ICC X over ICC Y is equal to the negative tangent of theta I. Right. So you should probably just write down this Feynman formula and skip all of that derivation because you probably don't need to do it. If you can just figure out that that's the formula you need. Then solving for theta initial, you can use A tan 2. So you just do A theta initial equals A tan 2 ICCX negative ICCY. And you get that theta initial is going to be equal to basically 107.08 degrees. Then we can use our final calculation, which is this formula right about here. We go yoink this and put this down here. All right. So we know that our final position or our final orientation is equal to our initial orientation, which is 107.08 or 1.87 radians. We'll do it in radians because better. So 1.87, which is our degrees in radians, minus our omega, because our omega is negative, because keep in mind we're doing a negative rotation, and that times 20, or delta t. And that solves out to basically negative 0.33 radians, or negative 18.91 degrees. That is a lot of math. Hopefully people understood kind of what was going on there. Yes, no, things you want me to go back on and explain how people feel.
Didn't you not answer the question? Which
What do you
is
mean?
the wheel did we do the wheel velocities? Did I
We
just
did
miss
do the
that?
wheel velocity. Oh, did we not do the wheel velocity? Did I skip over
That was
that?
like the first thing that it asks us to do. Is just
Oh, well,
I didn't even do it in the solution, I don't think, unless I missed it.
Yeah, no, I mean, we have omega, right? So we can just plug
Yeah,
omega
no, I
into
just
that formula.
yeah.
Sorry, my bad. I completely
okay.
skipped over that. Yeah, just plug omega back into VR and VL, and you'll get your answer. I can do the basic algebra, but I don't want to.
No, it's okay. I just was making sure that I didn't miss that you did it.
Nope. You're completely right. I just skipped over that. Sorry.
No, it's okay. And so that pi over 2 that we were given as like our initial thing, that's not actually what it was. We found it was like 100 or like 1.87 radians or something.
Say that again. I completely missed what you said.
So it says like in the question that like we're at 0, 0, and pi over 2, right? For like the initial orientation, but like our actual initial orientation was like the 1.87 radians.
Right. So it's not that your actual initial orientation was there. Your actual initial orientation is still pi over 2. But what that tells you is that you need to rotate your robot to that orientation in order to do the rest of the things. So in these questions, he generally says like, you can either, there's two ways to like solve that question. One is you either change the radius or you reorient your robot. Given that he wants the radius to be 8, I would reorient your robot. Right. So just like homework 2, I believe there was a similar problem.
Yeah, I think it was the same thing where he didn't want us to change the radius, but we could change the orientation.
Yeah, so you can change either one and both of them will solve the equations. It's just that changing the initial, just saying that you'll rotate the robot tends to be easier because then you don't have to worry about trying to like recalculate it.
And
cool,
so
any other?
The
Yes.
negative 0.33 radians.
That is your final orientation at the end of the arc.
Is that negative 0.33 radians from the x-axis or from the...
Yes. So all of these are with respect to the x-axis.
So then how... Because if it's negative radians from the x-axis, that means the robot is pointed towards quadrant 4, like down and to the right. So then how is it following the top arc?
Like that?
Oh, never mind. Yeah, I was thinking that it was the pose at the origin. That's my mistake.
Oh, no. Yeah, so your initial orientations look like this and that, which kind of makes sense, right? So it would look like this arrow right here and this arrow right here. That's like roughly tangent to the circle at those points.
Yep, that makes sense.
So hopefully that kind of makes sense as to why those numbers are what they are. Any other questions?
If we decided to change the radius, would we we'd first do like the negative tangent of our initial orientation and then kind of work backwards the other way?
Yeah, the way you would do that one is actually very similar to how you program. If you guys did the extra credit for lab 2, I would look at either find the way you did, like programmed it in there, or do the derivation, or find somebody else that did and use that derivation. I'm not going to cover it because it's like another whole process, but if you go look at your old code base, or like find someone and steal their code base for lab 2 for that part, like just look at how they've implemented it, because that's how you would do it if you change the radius. Because in your lab 2, you're not changing the order, the radius of the robot, you're just like sending it with that one. Cool. Any other questions? If not, we get to move on to the part I actually enjoy, which is graph theory. So much more fun. Oh my God. Okay. So let's look at the next question, which is, you are given, oh, wait, we're not doing graph theory yet. There's still another question. God damn it. Okay. Can you guys tell that I like graph theory and I hate everything else? It's okay. This one's pretty easy. So can I like draw a grid really easily in this? I don't know. Anyway, okay. So the question is, your robot must travel from the origin of your global coordinate system at a beginning pose of p start, which is equal to 0, 0, 0, to pose p end at 10 meters, 10 meters, and pi over 2. The robot must travel through the waypoints at W1 and W2 on its way from p start to p end. The orientation of the robot at the intermediate waypoint is arbitrary. Assume the forward velocity between any of two waypoints is exactly 1.5 meters per second, and assume a rotation requires 0.5 seconds. Cool. So let's go ahead and draw this out somewhere, and pray that it is easier to write than it will be. All right, so we have our XY. So our robot is initially facing at 0, 0, and 0. So that means our robot, I'll mark him in red. I will mark him in red. Cool. We have our robot. He's initially facing this way. His goal is to reach point 10 over 10. We'll label that in pink here, facing this way. And he must pass through some points. Give me 1 second. Let me draw some lines on this graph so it's like remotely easy to see what we're doing. Okay. 1, 2, 3, 4. Oh, look, my final point's already off. That's incredible. Okay. I'm going to delete those two. And then we're going to do the same thing this way. So 1, 2, 3, 4, and 5. Here we go. That is a grid, and we're going to pretend that it's even, and nobody has to say anything. Cool. All right. Now let's draw the final position of the robot. So our final position of the robot is right here, facing upwards at pi over 2. Is it pi over 2 or negative pi over 2? Let me double check. It's pi over 2. Cool. Yeah. Pi over 2. Cool. You have to go through 2 points. You have to go through 6, 6, and you have to go through some other point that I can't remember. Give me a second to look up. 6, 6. We'll call this, we'll call you W2. And you have another point here, which is W1, which is at 4, 2.5. So 4 and then 2.5. Okay. Cool. That is our path planning. All right. So the first question, what is the minimum distance the robot must travel to get from our start to our end? Should be relatively simple. We're just going to label these P start and P end. Cool. All right, what's the minimum distance? Well, it is literally the magnitude of each vector from point to point, or just do the Euclidean distance from each point. So we can just do our distance d is equal to the square root of our start minus our start, W1 minus start, W2 minus W1, and then Pn minus W2. So we'll just do, that is going to be 4 minus 0. So that's the x squared plus 2.5 minus 0. which is the y squared, plus this a bunch of times. I really don't want to have to write this out, but I will do it just for you guys. So that minus 4, that's our W2 minus W1 minus our y, which is going to be 6 minus 2.5 squared. That's all square root, plus our square root of our end to W2. That is 10 minus 6 squared. That's x's, plus 10 minus 6 squared. That's y's. Cool. If we solve that, we just get that is basically equal to 14.4 meters. Those are 9s. I have handwriting. 14.4 meters. Cool. Any questions on that question? No. The next question, that is Euclidean distance. Know how to take Euclidean distance.
The numbers, are those from the question or from the coordinate system?
Say that again.
Where did you get the 10 and the 6s and the 4s from? Again.
From the question and the coordinate system.
Okay.
The question specifies what P start, P end, and W1, W2 are.
Okay.
So it like, yeah, those numbers I pulled are not just out of thin air. Those are like from the question. So it says P end is at 1010 facing pi over 2, which is why the pink arrow goes up. Cool. So the next question is, what is the Manhattan distance the robot must travel to get from P start to P end? That is relatively simple. We'll call this part 2. All right, the Manhattan distance is going to be equal to your x's minus your x's plus your y's. So it's just going to be W1x minus P start x. So that's just going to be 4 minus 0. Then plus your y distances. So that's going to be 2.5 minus 0. That plus your W2 minus your W1. So that's going to be 6 minus 4 plus 6 minus 2.5. So that's for the y. And then that last, finally, it is P end minus the start. So we get 10 minus 6 plus 10 minus 6. You add that all together and your Manhattan distance is about 20. Cool. All right. So the next question is, how do we get a motion plan, rotations and translations needed to move the robot from P start to P end? What is along the shortest path? Remember, the shortest path must include the intermediate waypoints. All right. So the first thing we need to do is rotate the robot to face W1. How do we get that? We just do, all right. So step 1 is going to be rotate to face W1, right? So W1 is going to be, you do the tangent of the x's over the y's. Yes, yeah, that's math. Okay, or you do atan technically. So you do atan 2 of y over x, and that's going to be 2.5 comma 4. Oh wait, it might be the other way around. I don't remember how atan 2 takes inputs. We'll just use normal tangent. No to use atan 2 in your code, please. All right, tangent of y over x, which is going to be equal to tangent of 2.5 over 4. So that's your y distance over your x distance, which is basically equal to approximately 32 degrees. All right, then you need to travel forward the distance for W1. So your step 2 is going to be translate to face, translate or drive forward the distance between W1 and P start. So that is translate to between, or we can just do like the magnitude of the vector between W1 and like the origin. And that distance is going to be equal to the square root of 4 minus 0 comma plus 2.5 minus 0, and then you square both these things. All right, I'm not going to do the math for the other like 4 things, but I will explain to you what the plan is, and then I'll let you guys do the basic calculations because I really don't want to write all this out, and I don't think it's helpful. So is there anybody else that would like to see me write out all these calculations before I just decide to not? Does anybody particularly care about seeing these calculations get done? Okay, cool. I will take that as I can just write out the basics of like what you're supposed to be doing. All right, you
Arjun,
translate the, yes.
actually, I have a question, not really about like the calculation, just about like more like a theory type thing. So when you're like, well, I'm looking at like the solutions simultaneously, and you know, like the second rotation is like the 60.26 minus 32.01. So
Yep.
is that like the globally what the angle we should be facing is? It's not like we're supposed to rotate 28 degrees. It's like we should be pointing 28.25 degrees in reference to the x-axis.
Well, let's actually do it together, and we'll kind of get to that part next because I was actually about to hit there. So that next translation is actually pretty interesting. In this case, that 28.25 is actually relative to where you're currently facing. Yes, right. So the way we calculated that 60.26 is we took the tan of W2y and over W1y, right? And that gave us approximately 60.26, right? But the thing is, if we were to tell the robot to rotate 60.26 degrees, what would happen is it would way overshoot our actual mark. 60.26 is where we want to be facing relative to global reference frame, right? And 30.01 is where we're currently facing because we drove from our W1 to P start in facing that direction. So if we subtract that from our 32.01, then we get 20-ish degrees, or that 28 degrees. Is that what that says? Yeah, 28.25, which is our, like, how much we need to rotate. That makes sense? So 60.26, that first number in that rotate function in his answers is the global like reference frame. So essentially like with respect to the x-axis, what direction we need to be facing. That the second number is where we're currently facing, and 28.25 tells us how much to rotate.
How much to rotate to face that 60?
Yep, exactly.
And also, should that be for your tan? Is that W2y over W2x? Or is that W2y over W1y? Or that's what it says?
Oh, sorry, that's supposed to be W2y. Yeah, you're right. Or W2x.
Okay.
There we go. Sorry. Yeah, so essentially you're like, how do I face the current direction? How do I like, where is that point that I need to face? And then how do I rotate so I'm facing that point? And so that's what that calculation is. So you then rotate this amount. Your next step is to just drive forward the distance between W1 and W2, which is 4.03 meters. And then for your next step, it is rotate so that you are facing Y2. So basically we're right here facing relatively like that. We need to be rotating, so we're pointing there. So that's a 45-degree angle because you're going from 6.6 to 10.10. So you just need to subtract. You need to rotate negative 15 degrees. Degrees are negative 15.26 technically. Yeah. And then finally you drive forward. You're going to drive forward the distance between P end and W2, which is 4 meters. Oh, sorry, not 4 meters. I can't read. It is 6 meters, 5.66 meters, right? So 4 squared plus 4 squared, square root of that. And then finally, you rotate so you're facing the right direction, which is 90 degrees. And that is going to be, you just do 90 minus 45, so you need to rotate another 45 degrees. Cool, that is part C. All right. The next step is, the next part of the question is going to be, how do you do the same thing that we just did, but move along the Manhattan path? Does anybody want to see me super go through all this, or can I just give a very quick high-level overview of this so we can get to the path planning stuff? I will take the silence as I can just give a quick high-level overview. All right. So your goal is you're facing this way. If I were you, I would be lazy and I would not change the orientation of the robot unless I have to. So just drive forward your 4 meters, then rotate 90, go up, then up 2.5, rotate. I would actually keep going the same way. So you can go up 2.5 and then, well, I guess if you're doing Manhattan, you can do X, Y, X, Y, X, Y. his answers say going X, Y, then you do X, Y, X, Y. For like optimal Manhattan path, I would avoid rotation at all. So you go up, up, sideways, sideways, and then up. But both are technically correct, I believe. So either way will work. You will do the Manhattan distance. But let's stay consistent with his answers. And in the test, I recommend you stay consistent with his answers as well. So in this case, we're going to go up. We reach W1. We're going to rotate -90 because we are currently facing this way to face this way. We then drive the 2 meters this way. Then we rotate 90 degrees to drive up the 3.5 meters to face W2. From W2, we rotate -90 again, face this way, drive the 4 meters here, rotate 90 degrees up, and then drive up till there. Simple? Make sense, people? All right. The next question is, what is the time for the shortest path between your Manhattan distance and your shortest path? So between parts, your time for part 3 and your time for part 4. So
Cooper,
Yeah, I'm. It looks like Arjun is not here. Okay. Um. I zoned out for a bit, so I do not remember exactly which part of the problem he was on.
We were doing part E for number 2.
You know you disconnected, right?
yeah, I just disconnected.
Oh,
I
he's
just
back.
figured it
Okay.
out. I am back. I'm sorry. Z came running over. How long have I been disconnected for?
About a minute.
Okay, cool.
Yeah,
What
you
did
were
you guys
about to
miss?
start 2E. Literally, you were literally about to start talking about it, and then you stopped.
Oh, cool. Okay. I love Zoom. Zoom is high quality. Okay, hold on. Let me share my screen again so people can see what I'm doing. Only the host can share in this meeting. Motherfucking permissions. Okay, participants. Ezekiel and okay, now it is Zeke. Zeke is now Zeke, and I am now Zeke. So ignore. Wait, did I give Zeke the right co-host? Hold up. Okay, where were we? Okay, so what's going on? Let's see. Oh my God, they're just Fs. Jesus Christ. Okay. All of you are the worst. Okay. So we're doing part E. All right. Quick question that I guess I should double check. Okay. How long does it take to get between W1 and W2 for the shortest path versus the Manhattan distance? Okay, cool. That part's pretty simple. For the shortest path, what we are doing is handling our rotation. So there's some rotation at the start of our W1. So that is going to be 0.5 seconds. Then we add that to our distance between the 2 points, which we calculated earlier. That is 4.03. Divide that by our speed, which is 1.5. And we get an answer, which is 3.19 seconds. All right. That is for shortest path. All right. And then our Manhattan.
When you
By
say
the way,
shortest path, do you mean like the shortest
So-
of distance.
Right. So shortest path as defined by the question. So the question kind of defines shortest path as going from like the fastest way to get from one point to another, but assuming you travel through all the waypoints, right? So if we're following our shortest path algorithm in that case, it's kind of weird to explain. It's basically the Euclidean distance between each point in this question, right? So it's kind of up to the question how to define it. But if you read the question, kind of, it says like, I think, what is the motion path needed to move the robot from P start to P end along the shortest path? Shortest path meaning what is the shortest possible distance? And then remember that the shortest path must include the intermediate waypoints. That means you have to hit W1 and W2. That makes sense of what shortest path is.
Yeah. I mean, like it makes sense that you would use like the smallest forward.
Yeah,
distance.
it would just in this case, if like you're trying to calculate the shortest path between any 2 points, the shortest path is generally just the Euclidean distance between them.
And is the where did the 4.03 come from?
The 4.03 is the distance between W1 and W2, which you have right somewhere. It is just this right here. Right. So the square root of W2's point y is minus W, or W2x is minus W1x plus the square root of, that should be a plus, by the way, plus the distance between the y's. So the Euclidean distance between W1 and W2. All right. In that case, for the Manhattan path, it's just going to be this same thing. So we have one rotation in there during the movement. And then you have your 2 points, like your two distances, which is 3.5 plus 2 over your speed, which is 1.5 meters per second. And that gives you roughly 4.17 seconds. Cool. Any questions on that part about some basic path planning? If not, give me 1 second to like take a sip of water, and then we will go ahead and get started on the fun stuff, which is the wavefront algorithm. Also, I'm changing my name back to I stole this. Okay, cool. Finally, onto the exciting stuff. How do you guys feel so far? Does everything I've said make sense? Do you guys feel confident about those two sections of the midterm? We can take like a 2-minute break, so one, my voice heals, and two, I give you guys some time to give me any feedback. Cool, I guess not then. I guess we'll just keep going with the questions. All right. Our next question is exercise 3, which is the wavefront algorithm on a map. I'm not sure what the best way to do this. I think honestly the best way for me to do this is just really quickly like, here, let me open up the midterm prep and scroll down, and then we'll just do it on this map here because it will save us like a shit ton of time. All right. So the question is, given the following configuration space, determine the path between the start cell S and the goal cell S using the wavefront algorithm and assuming a 4-connected grid. Fill the diagram with the values determined by the wavefront algorithm and annotate the paths from start to goal. So basically, the wavefront algorithm is like as close to breadth first search as you can get it. Just the only thing to keep in mind is it's kind of like a breadth first search from the goal instead of from the start. So just remember that you would have to start from the goal and annotate the path from start to goal. Yeah, so you have to start from the goal in this case. So as normal, you set all your walls to -1 or some value that's like negative, so your algorithm doesn't touch it. Those are supposed to be -1s. Let's pretend that anything that is gray is a -1. All right, cool. And then the next step is just putting in our weights, right? So at our goal, we have a weight of 1 because that is a distance of 1 from itself. And then we can kind of just start adding in numbers. So you do 1, all neighbors of 1, then gets a +1. All neighbors of 2 gets a +1, so we get 3. All neighbors of 3 get a 4, so that's 4. And now the question is, where do we put our 5s? So we have 2 neighbors, so both of those get a 5. In this case, then all of the neighbors of our 5s get another 1 added to it, so we get 6s. You do the same thing with their neighbors, you get 7s. across these diagonals. 8's up here. And remember, we're 4 connected, so you can't do this diagonal right here. That has to be separate. So then we do all of its neighbors. So we get 9, 9, and 9. All of those neighbors get another one added. So we get 10, 10, and 10, and 11. Same things with 12. And then they finally meet up, and the start node gets a 13. Any questions? It's a pretty simple algorithm. Just keep in mind that you should be starting at the goal. Cool. Let's go ahead and move on to the last problem, which is the greedy breadth first search, Dijkstra's algorithm, and A star. Oh boy, this is the fun one. Okay, so all right, let's see. What's the best way to kind of show this to you guys? I'd honestly want to kind of just like draw on the map itself, but all right. So we're starting off at this point here, and we are going to Zerend. Okay. So let's go ahead and do a greedy breadth first search. To do it, I think our best way is to just write our nodes. So we're going to write a list here. We're going to call this node. And then we're going to write another list next to it. And that's going to be our cost function. So that's going to be h of n. All right. So let's see. Let me double check one thing before we start. Here we go. That's so the important thing you need to do in this case is we need to use this graph at the bottom here to kind of get our values. So I'm going to go ahead and move our, I can't show both at once, but know that when I pull a number out of my ass, I'm pulling it from this graph right here, or this chart right here. Cool, because our h of n is like an estimation from one node to our current node, and that's what this chart represents, right? So it's saying the distance from our target node being Zerend, for any one of these cities is this distance right here, right? So this is our h of n function, even though it's a chart, basically a lookup table. Cool. So let's start. We are at h, so we add h into our thing, first of all, and then we add our h of n, and our h of n is 459. Cool. Then we add in our two neighbors to, actually, let me draw the queue so we can kind of show what's going on here. I feel like I need more space. All right, let's draw this down here. So we're gonna have our queue here. Actually, here, let's do this. We'll do our nodes. We'll have the h of n function for those nodes. And then we will have like our final nodes here, right? So this is going to be our final. These are going to be our explored list. This is essentially the answer will be explored. And then we will be adding nodes into this queue right here, right? So this will be our priority queue. And this will be our explored list of nodes. Okay, so this will have our node n and our cost h of n. Okay, so step one of all searches is you put your start node into your priority queue. So you put our node h in here, and then you put the cost of, which is 459. Our next step in the algorithm is we pop the first item off the queue. So that means we take h out and we put it into our explored list. So that means h goes here, their cost is 459. And then we add in h's two neighbors into the list. So our two neighbors are going to be E40. So we're going to call that node E. And E40 has a cost of 625. And we're also going to add in I cannot pronounce any of these names. I'm going to call them by their first letter. U, and U has a cost of 450. We got these costs again from this table right up here. That's where we're pulling these from. So h of n is now out of our function. And now the question is, what node do we explore next? And the answer is always choose in a priority queue. You're choosing the one with the lowest cost. So now we explore U. So we're going to explore U. That means to put U in explored. So U has a cost of 450. We take it out of our queue and we add in U's two neighbors, provided that they are not in explored. So in U has two neighbors. It has Bucharest and it has Lucy. Remember, in this case, we're going to go in alphabetical order. So then the next things we add in are going to be B, which has a cost of 432. And we have Lucy, which has a cost of 475. Cool. U is now in here. Start back at the top of the algorithm. What is the lowest cost node in our list? It is B. So we take out B here, put that into explored, which is going to be, what is the cost of that again? It is 432. And then we add B's neighbors. So B has 1, 2, 3, 4 neighbors. Yes.
So if I think it was V, if V had a lower cost than B did, would it go down that path even though it doesn't leave to like the Zerend?
Yes.
Okay.
Yes. So the algorithm doesn't really know what the graph looks like. If it did, we wouldn't have an entire study of computer science devoted to it. The idea is that we don't know what the graph looks like, and we can only rely on these H of N function. That's all we have. So we're going to try exploring that way because that way seems closer, but then we might find out very quickly that it doesn't reach at all.
Gotcha.
So if V was lower, we would explore V, and we might explore V later. We'll see how the algorithm goes. All right. So now that we are exploring B, we have to add B's 4 neighbors. And remember, we're going in order. So what comes before? Does G come before F or does F come before G? A, B, C, D, E, F, G. Okay, F goes first. Okay. Listen, man, I know how to do CS. I don't know how to do English. All right, so we add our node F. F has a cost of, it doesn't actually matter where I put them in this priority queue. I'm putting them randomly so we save space. But keep in mind that the priority queue would actually sort them by this H of N function here. So like technically I should be moving them around, but I really don't want to have to like write each node like 10 times because we'll be here all week. So F in this case has a cost of 279. The next node we're going to add in is Gigoru or G. So we're going to put in G. G has a cost of 462. And then we need to add in Peresti, and that is P, and that has a cost of 326. And then finally, we need to add in Yerzini. But keep in mind, we've already explored that, so we don't add it into our queue. That is the important thing to keep in mind, that you do not add nodes that you've already explored into your queue. All right, we've added all their neighbors. Now we need to find out what's the next neighbor to explore. You choose the lowest one. In this case, it's F. So I'm going to move F to our explored nodes here. And I'm going to remove it from my nodes. And now we're going to add all of F's neighbors in. All right, so F. F has 2 neighbors, easy peasy. We've already explored Bucharest, so we're just going to go straight to Cebu. And so we're going to add node S here, and that has a cost of 209. All right, there are no other neighbors of F, so we're going to go ahead and call that a day. And now we're going to go ahead and add in, run the algorithm again. What's our node that we're pulling out? We're going to pull out node S because it has the lowest cost. So we move that to our explored nodes. S of 209. All right, so now we need to add in all of S's neighbors. S has 1, 2, 3, and 4 neighbors. So we need to check each one of them. We first add them in alphabetical order. So we're going to add in Arad. That has a cost of 51. You're then going to add in Oradea, which has a cost of 70. What's next in the letters? We should then check F because F is next alphabetically. F is already in our explored node, so we don't need to add it. We next add in remove. I can't say these names. We're just going to call him R. We're going to add in node R. R has a cost of 278, as we can see up here. And then finally, we're going to add in Oradea, which has we're going to call O, and O has a cost of, what does it say? 54. Cool. That is the algorithm. We have now finished up that node. So now we need to explore our next node in the list. This is our target. I'm going to remark that. Cool. Our next node in the list is the one with the lowest cost. So we're going to explore A. A has a cost of 51. All right. A has two neighbors. It has Zarin and Timisoara. So Timisoara, we're going to add that one in first because it starts with a higher letter. That cost is going to be 91. And then we're going to add in Z. Z has a cost of 0. And that is now in our queue. So we're done with that node. And now finally, it is explore another node. And in this case, we pull out the lowest cost. The lowest cost is Z. We add it to our list. That is our target node. So the algorithm is done. And we have done a greedy breadth first search. Does that logic make sense to people? This is probably the most tricky part of the midterm and what most people mess up. So let me know if you have any questions. We all good? If so, I'm going to go ahead and I'll leave this on screen for like a second or two, and then I'm going to go ahead and erase it so we can do the Dijkstra's algorithm. Cool. In that case, let's move on to Dijkstra's algorithm.
Question.
Yes.
Okay, so this isn't on the specific exercise, but this is the exam. So do we have 8 a.m. to 12 p or like midnight to like work on the exam, or is it like we can start the exam anytime and it's only going to be an hour? Like it's going to be
No, you have all day to work on this.
Okay.
You can. Yep. Yeah, he's being really nice to you, so have fun. Yeah, I think he said it should take a couple hours if you don't know what you're doing, and like an hour if you do, if I remember his quotes correctly. So you guys should be okay. I have confidence in all of you. Okay. Anybody else want me to leave this on the screen for any longer or any questions? If not, I'm going to go ahead and start on the Dijkstra's algorithm. Cool. I'll take your silence as approval. Okay, next part. Do part A, but with Dijkstra's algorithm. Cool, so let's use Dijkstra's algorithm. Let's make our charts. So in Dijkstra's algorithm, we're going to do the same thing. We're going to have our explored. And we're going to have our nodes here, and then our function. Dijkstra's algorithm, and from what you guys have learned in the class, the standard name for the cost function is g of n, so we're going to go ahead and stick with that. And then we're going to write our priority queue down here. Actually, we should do it like, maybe if we do it up here, we still can't see anything. Okay, cool. This is going to suck. Queue. Cool. And then this is going to be our nodes.
Arjun, maybe it's easier to like just use the solution and just talk through the logic of the solution instead of rewriting it all out.
The thing is, the solution doesn't really show the like intermediate steps of getting the algorithm, which is kind of why I want to make sure you guys have that.
Yeah, that's fair.
Right. So that's why I want to work it out. So this is going to be a node. Oh, wait, we're doing Dijkstra's algorithm. So we need to do something slightly different because we need to keep track of the path cost, right? So we're going to call this path P. What did I do? Okay. Yeah, so we're going to call this path, and then we're going to call this edge cost, and then we're going to call this. Right. Okay, so there's going to be slightly different organization. It's just because we're using Dijkstra's instead of the greedy breadth first. So we're going to have a path. We're going to have a the edge cost, which is going to be the cost on the graph, plus our g of n. Okay. And do I have that right? Yeah. Okay. And then we're going to have our priority queue here, which is the same thing. Or well, this is just going to be Q, which is going to have nodes. And then this is going to have our g of n. Do I have this explained right? All right. Cool. All right. Let's go ahead and get started with Dijkstra's. So same step as always, we add in our first node. So that's going to be h. The distance from our node is going to be 0 because we are at the start node. That is our start node. So we're going to go ahead and pop that off our thing. So we get our path, which is 0, our node that is 0, our path, which is h, like h, and then we get our edge, which is 0, and then we get our g of n, which is going to be 0 as well, because distance from g to n is 0. All right, cool. The next thing we need to do is we're going to add in our 2 neighbors. So our 2 neighbors in the queue are going to be node E, and node E has a g of n cost, which is the path cost of 86, and our node U, which has a path cost of 98. Cool. Then the algorithm goes, what node should I explore? And the answer is always the one with the lowest cost. So in this case, we explored node E, even though it's completely in the wrong direction. All right. So our edge cost is going to be, so our path that we're now exploring is going to be HE, right? So what I'm doing is I'm saying we're going from H to E. Actually, you know what? I want to structure this in a different way, so this kind of makes sense, because this is kind of putting it straight in the answer, and I don't want to do that. So I'm going to go ahead and erase this. We're going to start over, and we're going to kind of do this in a different way. So I'm going to do our explored list here, and I'm going to put in a couple things. I'm going to put the node. I'm going to put our path cost, our g of n, and I'm going to put came from. So this is the better way to calculate it while you're doing it live, and then you can kind of back formulate the answers. So, and then in my priority queue, I'm just going to put this. I shouldn't have raised my priority queue. Okay, well, we'll just rewrite it. Okay, our priority queue is going to have node, and then g of n, and then our path cost, right? So then g of n. Okay. Cool. Let's start again. So again, we're going to put in h here. We're going to have 0 and 0. That's the first step of the algorithm. Next step is going to be to pop the first thing off the list. There's only one thing there. So we choose that and we put in here. So we have h. The path cost is going to be 0 because we are at our starting node. Our g of n is also going to be 0. And then our came from is going to be null, right? So that's our, you can either do null or some other variable there to kind of identify that this is the starting node. Okay. So, okay. Our next step, since we've now popped h of n off, is we have to add its neighbors. So the 2 neighbors we're going to add in are 40. So node E, its path cost is going to be 86. And then its g of n is going to be its came from, or it's like g of n of the last node plus its path cost. So in this case, it's going to be 0 plus 86, which is 86. And then we are going to add the other node, which is node U, has a path cost of 98. And same thing, the previous node cost was 0, so we add 98 here. All right, cool. That's the nodes and the neighbors of that. So now we're going to go ahead and we're going to pop the node with the lowest cost. In that case, it's going to be node E. Remember, path cost of this is going to be 86. That means g of n, which is going to be the last node or it came from, 86. And then we're going to put an E here. Cool. So we're going to explore node E now. Node E has no neighbors. So we just pop it off here and we move on to the next one. Our next node is going to be node U. So we're going to put in node U here. Its cost is going to be 98. G of n is going to be 98. And it also came from E. So node U, we take it out of here. Now we need to add all of node U's neighbors. So in this case, there are 2. There's going to be node B. And there's going to be node V. Those stand for the cities, by the way, in case that's still not clear, but hopefully it is. Okay. Our path cost is going to be 85 for the edge, but we also have our g of n, which is the cost of the last node. So this is coming from node U, So we need to add g of n for node u, which is going to be 98. 98, and then we add that to our path cost. So that means our cost here is going to be the previous g of n plus path, which gives us a value of 183. Same thing with the v node. So we have our path cost of v. So from u to v is a cost of 142. G of n is going to be equal to the cost from the g of n of the last thing plus our cost of path. So that's going to be equal to 240. Cool. So that's the next step of the algorithm. Go back to the top, pop the node with the lowest cost. In this case, it's node B. So we pop off node B. Node B came from node U, and then we fill in our values of 85 and 183. We can erase this out of the list. Now we need to add all of B's neighbors into the list. Keep in mind, I'm not doing this like next to me, but it is very helpful if you just keep came from also in this channel. So what node added it in? In your code, you should do it that way. I am just being dumb and forgot to. But I'll go ahead and start doing it now because we might as well. Hold up. Let me move this somewhere. All right. I'll add a came from column, and we will add, this is coming from node U. Okay, cool. So back where we were. So we were on node B. We need to add all of B's neighbors. B has 3 neighbors. It has node F. The path cost from U or from B to F is 211. Our G of N, which is our last G of N from node B, is 183. So 183 plus 211, which should give us, if I can do math, what is that math number? What is 183 plus 211? I need a calculator. Hold up. 183 plus 211. Okay, that gives us 394. Okay, and then our came from, which is going to be node B. All right, the next neighbor that we have is node G. Node G has a path cost, if we look at it, of 90. Then we take the G of N from B, so we do 90 plus 183. That gives us 273. That came from node B. And our final neighbor is Pitesti. So we add a P. Its path cost is going to be 101. Its last G of N is also going to be 183 plus 101. That gives us a cost of 284. Our came from, in this case, is also going to be B. Cool. So we look at our list. We say, okay, what's next to explore? In this case, it's going to be node V. We can fill in our values here of 142 and 240. And this came from node U. All right. So node V. Node V has one neighbor. It is Lussie. So we have L. Node L has a path cost of 92. Its G of N is going to be 92 plus 240, which should be 332, plus it came from, and I came from node V. All right, that's its only neighbor. Go back into the algorithm. All of its other neighbors are already in our explored list. That is why I'm not acknowledging them. So our next thing is going to be going through and doing our lowest cost node. In this case, it's going to be node G. So we're going to add node G to our explored list. G has a cost of 90. G of N is going to be equal to 273, and G came from B. Okay. Any questions so far about what I'm doing? This algorithm is going to take a while. So we can keep going through this if you guys want, if there are any questions. If not, I'd like to skip just straight to A star because I think it'll just save us some time, given that we've already been here for like almost 2 hours. But does everyone understand the general algorithm that I am following? The only last thing I'll do is, let's say that G was our target node and you wanted to now reconstruct the path, which is the thing we'll have to do in A star as well. What you can do now is you can just kind of follow this came from that we have in our chart and kind of backtrack through it. So in this case, our path would look like G, then you'd look at came from, so that's a B, then where B came from, which is U, and where U came from, which is H. That sound good? Any questions on that so far? If not, let's go ahead and move straight to A star. If you keep following this general algorithm, you will get the correct answer. The only other thing to keep in mind is that if you, let's say you run onto a node, let me see if I can find a good example. Let's say you have Rimu Vikea already in the list, and then you run into it again while you're exploring like Cebu or something. The thing you want to keep in mind is that if your Cebu cost to Rimu Vika is lower than your Rimu Vika cost, you should update that node in your queue. And that's an important thing. I'm sure we're going to cover this again in A star, and you'll have a concrete example, but make sure you keep that in mind. If not, let's go ahead and move on to A star. Cool. Okay, so A star example, best time. Okay, let me just erase all of this. Okay, so we're going to set up the same chart. We're going to have our explored list. And we're going to have a couple different columns now because we're doing A star. So we're going to have our node name. We're going to have our G of n function. We're going to have our H of n function. And we are going to have our F of n function. And we're also going to have came from. Cool. I'm going to duplicate this so we can do our perfect. All right, and this is going to be our priority queue. Okay, so A star, same algorithm, exact same methodology, except this time you need to add G of n and H of n, and then you're evaluating F of n. So this is kind of the function that we are going to be popping is going to be this F of n stack right here. I'm just going to write them out separately, but in your code, you can just have G of n plus F of n as the thing that you're putting into the priority queue. Cool. So as always, we start by adding in our main node. So our H of n here. Our G of n in this case is going to be 0 because it's the start node, but our H of n, which is our heuristic or like our evaluator, that's going to be 459, which means our H of n is going to be this plus this. Our F of n is going to be H of n plus G of n, which is 459, and our came from is going to be null. Cool. We can pop that. We can put that into our list. We're going to have H of n here, G of n of 0, 459. Plus 459, and then our came from, which is going to be nothing. Okay, so we're going to erase this out of our list. Okay, so we've got that node. Now, the next step after we pop it out of our list is to add its neighbors. So we have two neighbors. We're going to have node E, and we're going to have node U. All right, so G of n is going to be equal to the path cost plus the G of n from the last code. So in this case, the path cost for E is going to be 86 plus 0, which is our last G of n. And our path cost for U is going to be 98 plus 0, which is our last G of n. And then we look at our H of n. So our H of n in this case is going to be 459, or no, sorry, my bad. H of n is just going to be from this table right here. So H of n for U is going to be 450. H of n for E is going to be 625. And that means our F of n for each of these, if we do the math, plus 625 equals 711. And our one for the other one is going to be plus 450. And our came from in both these cases is going to be node H. Oh, I wrote of n here. Sorry. Okay. Cool. That is that first step of the algorithm. So we're going to continue this again. We're going to choose the lowest cost node. In this case, it's going to be node U because U has the lower f of n. So we do U 98, 450, and f of n of 548. And that came from node H. So let's pop that out of our queue here. All right, so now let's get the neighbors of H, or the neighbors of U. So U has two neighbors. It has node V and node B. Since we're going in alphabetical order, we go B, then V. So B has a G of n, or a path cost of 85 plus the last G of n. So that's 85 plus 98, which is going to be equal to 183. V has a path cost of 142. So 142 plus our last G of n, which is 98. So it's 142 plus 98, which should be 240. Cool. Yeah, and our next thing is going to be our H of n. So our H of n for node B is 432. Our H of n for node V is going to be 475. So we go ahead and add those together. So we get 183 plus 432. You get 615. That came from node U. This one also came from node U. And then we get 240 plus 475. And we get 499. That's 699. I lied. 240 plus 475. I can't use a calculator. Plus 475. Cool. We have 715. Cool. So that's the complete step of our algorithm. So we go back to the top. Our option is pop the lowest cost node. In that case, it's going to be B. So we'll move over our stuff here. A thing to keep in mind is I'm moving it over to Explored before I write the rest of the code. But technically in your code, when you're implementing this in real life, you pop it, do stuff with it, then put it into Explored. That is the order that you do things in. I'm just doing it out of order so I can keep my data organized somehow. This is to keep in mind in case he asked you to implement like A* or something during that programming question, but I don't think he'll do something that hard. Cool. We are now looking at node B. So node B has 1, 2, 3 neighbors that aren't explored. U is already explored, so we don't need to worry about him. Cool. So let's start off in alphabetical order. Node F. Our G of n of node S is the path cost, which is 211 plus our last G of n. So that's 211 plus 183. That is 384, or 394, sorry. Our H of n for node F, which is going to be 279. And that gives us an F of n of 394 plus 279 equals 673. And our came from is going to be equal to B, because that's node we got it from. Our next node that we're adding is Patesti, Gigaru. Okay. Gigaru has an H of n cost of 462. If I can read right, its path cost is going to be 90 plus the last path cost, so 90 plus 183 gives me 243. We didn't add those together, so we get 243 plus 462, which gives me 705. And that came from is going to be equal to B as well. And then finally, our last friend node, which is Patesti, so that's P, has a path cost of 101 plus 183, which is our previous G of n. That's 284. And then our H of n is going to be our heuristic here. So that's H of n should be, we're doing node P, so that's 326. And so you do 284 plus 326. 284 plus 326 gives me 610, and that came from node B. Cool. The next question is, what node do we explore next? That answer is going to be the lowest cost node. In this case, it's going to be node P. So let's move over all the data to our explored list. 284, 326, and 610, and that came from node B. All right, and let's take it out of our queue. All right, taking it out of our queue, the next part of this algorithm is then going to be adding in all of our neighbors of P. So we have two neighbors of P that we haven't explored. That is node R and node C. We'll start off in alphabetical order. And so we're going to go with node C. The path cost of node C is 138 plus our last G of N cost. So that's going to be brain. What did I say that number was? 138 plus 294, 284. So our G of N is going to be equal to 422. Our H of N is going to be equal to node C, which is 315. And this came from node P. So we do 422 plus 315. That gives me 737. Okay. The next node that we're looking at is going to be node R. So we're going to call him node R. R has a G of N, a path cost of 97. We add that to our previous G of N for node P, which is 284. We get 381. Our H of N for node R is going to be 278. We add those together, so we get 381 plus 278, which is going to be equal to 659. Then we're going to be doing our came from. Our came from is from node P. Those look like P's. They do not look like those. Okay, cool. Node P, and those are all the neighbors of Potesti that we have not already explored. Okay, so what we're going to do next is we're going to pop the lowest cost node off our list. In this case, our lowest cost node is going to be node R. So we're going to move node R over here. So node R is going to be 381, 278, and 659. And it came from node P. So we get rid of this, this, and this. Cool. Now let's add all of R's neighbors. R has one neighbor, two neighbors actually that we need to check. The first thing we need to check is node C. So R has a path cost. What we need to check now is that the f of n function for node C is not lower than the f of n function from the different path that we found earlier, right? So in this case, we need to check that if coming from R, from our start node, is cheaper than coming from P, do we need to update C? So in this case, what we need to do is do the same thing. So we do 146 plus our path cost, or our path cost, which is 146, plus our previous G of N, so 146 plus 381. That gives me 527. So it's like, I'm going to put C in twice here. This is just so we can like understand what's going on, but keep in mind that it's only ever going to end up here once. We're going to take out one of these in a second. Our same H of N cost, and this came from node R. So now the question is, which one of these do we keep? And the answer is always the one with the lowest cost. So if our f of n for this node C is lower than the f n for this node C, so if node C from R versus node C from P, we would keep the one with the lower cost. In this case, the one from P is lower, so we keep that one. But if the one from R was lower, we would replace the P one with the R one. Does that make sense? That's a very important thing that he might try to get you on in the exam. I will take your silence as yes. Cool. Let's go ahead and then look at our next node. Our next node is going to be node S. Node S has a path cost of 80, 80 plus our last path cost, so it's 80 plus 381, which should be 461, plus our H of N for node S, which is going to be 209. And that came from node R. Cool. If we add those two together, we get 461 plus 209. We get 669. And then we run the algorithm again. So what node are we going to explore? We're going to be exploring node F because that's the one with the lowest cost. So let's pull that out. Oh crap, I need those numbers. Okay, hold up. That's going to be 270, 394, 279, and whatever, what was the addition of that? 673. Okay, so it's 394, 279, 673, and that came from node B, if I remember correctly. Let's pray I'm right. I think so. Okay, let's pop that out of here, and then let's add its neighbors. So our one neighbor of F that we're checking is going to be Cebu. So I'm just going to do the same thing I did last time, which is I'm going to add another S in there, and then I'll choose which one to keep. So that has a path cost of 99. We can add that to our previous H of N, which is going to, or our previous G of N, which is going to be 394. So we got 493. Our H of N in this case is going to be the same as before. So it's a 209, and that came from node F. We can look at what our F of N would be equal to. This case, our G of N is bigger and our H of N is the same. So I know that this bottom node is a higher cost. So we're not going to keep that in the list. So we're going to check that out. Cool. And now we're going to explore the next node in our list. That case, it's going to be node S, which has a cost of 669. So we're going to do S is equal to 461, 209, and 669. And that came from node R. And we're going to go ahead and remove this out of our list and add all of its neighbors. We're almost done. Cool. S has two neighbors that we need to care about because we have not explored them yet. So that is going to be node O and node A. So we'll start off with A. A has a path cost or a distance of 51. So we'll call that put that in for H of N. Its path cost is going to be 140. We're going to add that to our previous H of N of 461. So we're going to get a 601. Our F of N is going to be equal to 652, and it came from node S. Let's do the same thing for node O. So we have node O. Its H of N, if we look on our list here, it's going to be 54. Its path cost is going to be 151. We add that to our previous H of N of 461. So we're going to get a 612. We can then do 612 plus 54 to get our F of N, and that's going to give us a 666. Boo. And that also came from node S. Cool. That's the end of that loop of the algorithm. Next question is, what's the next node that we pop? Next node that we pop is the one with the lowest cost, as always, and that's going to be node A. Node A is going to be 601, 51, 715, and node S. Cool. It came from node S. We're going to pull this out of our list here. Okay, so we have node O. So we're going to put in the neighbors of node A that are close to the thing. So we have node Z, which has a distance H of N of 0, but a G of N, which is going to be the path cost of from A to Z, which is 75. So we do 75 plus our previous G of N, which is going to be 601. And we get 676. That means our F of N is going to be 676, and this is going to be node Z. And that came from node A. Fortunately, we're not done just because we added a list. We need to keep running the algorithm as is. And in this case, we're going to notice that node O is the next one to get popped. So we're going to put O into our list. O came from S, and there's cost 666. Its H of N is going to be 54, and its G of N is going to be 612. Okay. So we need to add all the neighbors of O. To do that, what we're going to do is look at our chart. The only neighbor of O that we haven't explored is Z. So we're going to do the same thing that I did earlier, where we're going to add another Z into this list, double check that it's not a lower cost. And if it isn't, we can move on. So the path cost is going to be 71 plus our previous G of N. So that's 71 plus 612. That gives us a 683. Our Z of N, H of N is 0. our z h of n is 0, and that means our final cost is 683 from node O. Cool. Keep in mind, we're only going to keep one of these. In this case, we're going to remove the bottom one because cost is higher. And finally, the last step of our algorithm, we're going to put node Z into we're going to pop the lowest node. Lowest node is node Z. We can finally get rid of our list. This is our target. So that means the algorithm is done. We do not need to run it anymore. And Z had a cost of like 67, 0, and 676. And then it came from node A. Cool. We've found our node. But the question is, how do we generate this into a path? And the answer is the same as always. We start off at our target node in our explored list, and we reference backwards, right? So we go from Z to A, and A to S, and S to R, right? So we're going to write this out. It's easiest to write it, so you just do Z. So we did Z. We get the came from Z, which is A. So we then look at A. A came from S. So we get S. S came from R. So we put R down. R came from P. So that's P. P came from B. So we put B. B came from H. Or B came from U. And U came from H. And H came from nothing. And that means that is our full path. And this is the path that A star found. And I did it right. So we didn't screw up majorly. That is A star. I understand it is a tedious ass process. Nothing on the test will be nearly this difficult. Are there any questions about what I just did? Is anyone awake? I understand that was boring as all hell.
We're here.
Cool. I'm sorry that took so long, but hopefully that kind of brought some clarity of exactly how to do this. Nothing he gives you should be this difficult, because this is, or like not even difficult, more just this tedious. Because this was kind of just like a pain to get through because it was so long. But if you can do this, you will be set for the midterm. Cool. I don't have anything else to cover. If there are any other questions that people have, feel free to let me know.
Is there any coding stuff you want to quickly go over that might help us?
I actually have no idea what he's asking on the quiz tomorrow. If you guys like want, we can do like a little bit of Python if there's any parts of Python you're confused about in particular. Like is there any section in particular you'd like me to cover about like how Python works or the syntax for it or something like that? My recommendation would be understand how to import things, understand how to do methods, understand how classes work. That would be a big one. I know some people tend to get confused on that, but if you can do all those things, you should be okay. Make sure you understand how ROS-Pi works. I'm just thinking of things that he might throw you. He might try to throw like some ROS-Pi stuff. So if you're not familiar with how ROS-Pi and Python work together, you might get tripped up on there. So make sure you review your like lab code or something just to make sure you have the syntax right and you don't like mess up how to find a publisher and subscriber and stuff like that. But yeah.
And look over homework 1. Anything that was on homework 1 is fair game. So stuff like recursive calls, knowing different data types like dicts, queues, all
exactly.
that.
All right, so I'm gonna go ahead and stop sharing my screen. Let me start my video here. Yeah, any other questions? I could go over something if you have a specific question for me to answer. I can go over something if there's a specific question you have for me. If not, best of luck tomorrow. You guys will do this. You guys got it. If not, I think that's the end of the session. But good luck tomorrow. You guys got this. I believe in you. James and